So before watching this lecture, you should know about hypothesis testing when we have one restriction applied to the linear regression model with several explanatory variables. In this lecture, we'll extend this and we will allow several restrictions. The test will then become an f-test instead of a t-test. The setup is the same as for the case when we had just one restriction. That is, we have a linear regression model, random sampling, and Gauss-Markov assumptions. So we have this model, and to do inference, we have the normality assumption on the error terms. As a concrete example, let's use the same example as in the lecture with one restriction. So we have the final result explained by SAT verbal section, SAT math section, and the high school GPA. So we have this final, the SATV, SATM, and the GPA, and the interpretation of the beta parameters. Well, at least for the slope parameters. So previously we have looked at this hypothesis, beta 2 equal to 0. So let's say I want to add more restrictions to my null hypothesis. I might want to add beta 3 equal to 0 and beta 4 equal to 0. And comma here should be interpreted as and. So I want to test all of these restrictions at the same time. Is it true that beta 2 is 0, beta 3 is 0, and beta 4 is 0? This is a very common hypothesis. Notice that I have not included the intercept into this null hypothesis. There is no beta 1 here. So let's talk for a second about what it tests. So first of all, what would it mean for this null hypothesis to be true? Well, you can see that if it's true and all these slope parameters 0, then yi, the result on the final, is just an intercept plus an error term. That means that none of my explanatory variables will have an effect on the expected final result. So this hypothesis basically says that my model has no explanatory power whatsoever. So before continuing your analysis, this is an hypothesis that you really need to reject if you want to be able to take any other results seriously. So let's look at how we can test this hypothesis. So in general, we have the following setup. I want to test if beta 2 is 0, beta 3 is 0, and so on, all the way to beta k is 0. I'm not including the intercept. I am allowing the intercept to be non-zero because I'm really interested in figuring out if the explanatory variables have an effect. So this is a hypothesis with more than one restriction. You can see that we actually have k-1 restrictions. In our example here, we have 3 restrictions. So you cannot test an hypothesis with more than one restriction with a t-test. So we have to leave the t-test and we will instead consider the f-test. And to do the f-test, the first step will be to calculate an f-statistic. So the null hypothesis, this one, we have k-1 restrictions. And we claim that none of the explanatory variable has a significant effect on y. The strategy for performing this test is basically the same as the t-test. That is, we calculate the test statistic, we find a critical value, and we compare these two. The difference is that now we have an f statistic instead of a t statistic. The f statistic is calculated according to this formula. So it basically only involves r squared, k, and n. You can see that there is a direct relationship between this f statistic and r squared. The higher the r squared, the larger the f statistic. And we know that the high r squared means that we have a good fit. And that in turn means that we should reject the null hypothesis if this f statistic is large enough. And what is large enough? Well, in econometric statistics term, large enough basically means that we're deep into the tail of the distribution. So we need to find the distribution of this f statistic, and we need to find a critical value, which tells us when we are in the tail. So fortunately, one can show that this f statistic has a very nice distribution if the null hypothesis is true, and that is it follows an f distribution. Under the null, it follows an f distribution where the degrees of freedom in the denominator is k minus 1, and the second degrees of freedom is n minus k. So this test is so important that the value of this f statistic is presented by all econometric software. In Gretel, for example, you find it here. That's the f statistic, or the f value for this null hypothesis. In eViews, you find it here, f statistic. If the null hypothesis is true, this number should be viewed as a drawing from the f distribution with 3 degrees of freedom and 95 degrees of freedom. Notice this is precisely k minus 1. We have k equal to 4 in our case, and this is precisely n minus k, 99 minus 4. So is this number deep into the tail of the f distribution? Well, all we have to do is to find the critical value. So let's do that. Let's do the critical value. So bring up the statistical tables, the f distribution. We need 3, 95, and let's define the tail as having a weight of 5%, level of significance. Well, then the critical value is 2.7. So anything beyond 2.7 is in the tail. So this 8 points, okay, I'll switch to eViews. Let's switch to Gretel again. This point here, 8.455 something, is deep into the tail, and the null hypothesis should be rejected. So let's state all this formally. We have an f statistic. We know that the f statistics follow an f distribution under the null. So to test the hypothesis, all we have to do is decide on a level of significance, that is the size of the tail, and reject the null if you're in the tail, that is if your f value is greater than this critical value. All hypotheses can be formulated in terms of p-values instead, and this is no exception. So for this hypothesis, we define the p-value simply as the value of alpha, where our f value is equal to the critical value. This p-value is also presented in all econometric software. So for Gretel, you find it here, practically 0. So again, that tells us that you should reject this null hypothesis. It is not true that all the slope parameters 0. And in eViews, you find it right below, right there. Now, this is not the only possible test that you can perform which has more than one restriction. You can do basically anything. You could test an hypothesis, for example, something like that, this beta 2 equal to beta 3, comma, beta 4 equal to 1. This is a hypothesis with two restrictions, one here and one here. So we need the f-test to do it, but we typically don't have to worry about the details here. We can just ask an econometric software to do it, and this software will produce a p-value for this hypothesis, which will then allow us to make a decision. So in Gretel, you would do the following. You will go to, so I want to test this hypothesis. Go to tests. This is a linear test, linear restrictions. The first restriction is that beta 2 is beta 3. That's the thing we have here. Beta 2 minus beta 3 is 0. And then you just simply type the second restriction on the next line. So that would be B and HSGPA equal to 1. Okay, and you get the F value right there, and you get the P value right there. So this should be rejected at the 5% level. In eViews, you would go View, Wall Test. You would write C of 2. You can actually, you don't have to move that to the left hand side, so you can do C of 3. And you don't have to do a new line, you can just do a comma for the second restriction. So C of 4 equal to 1. And that will give you your F statistic and your p-value. Well, it turns out that you can actually test this hypothesis with another test, which is a chi-square test, and we'll come back to this test a little bit later on.